Alright, so if I had a rectangle whose length is 5 more than its width, what are the dimensions of a square that I can add to make the rectangle a square? You may move any parts of the rectangle, but you may not get rid of any pieces. Make sure to keep the equation balanced. Alright, so let's look at this. So there's a couple things I can do. Let me redraw this. So I have a rectangle that is x plus 5 halves plus 5 halves, which is just x plus 5 by x. And one of the obvious ways to make this a square that many people jump to is, oh, we'll just add 5 here to the bottom, so it's x plus 5 by x plus 5. The problem I have with that, if you redraw this, if this is x and this is 5, is that now I'm not adding a segment here that has a variable base, and so I'm adding more variables to the equation. So ultimately what I'm trying to do is to add something that doesn't give me more of the unknown quantity. I just want to add something that's known to the equation to complete the square, to make the rectangle a square. So that doesn't work, but let's see what we have here. Just algebraically I'm going to trace this as well. So we have the area of this rectangle is x plus 5 by x, otherwise known as x squared plus 5x. And I want to make this a square geometrically and a perfect squared trinomial algebraically. So what the trick here is, so I take half of my known quantity, which is 5, and I chop off an area here which is 5 halves by x. And I'm not going to get rid of it, but instead what I'm going to do is I'm going to rotate it and place it right here. So the 5 halves has been rotated as well as the x side, and so it lays just like that. And so now I have this almost square, and it would be a square if only I could fill in this piece. Now what's the area of that piece? Well, I know this is 5 halves here, and this is 5 halves here, so that must be a 5 halves by 5 halves with an area of 5 halves squared. So by adding a piece with an area of 5 halves squared, I have made this now a square that is x plus 5 halves by x plus 5 halves, or x plus 5 halves squared in its area. So how do we translate that to our algebra? Well, we took this area of x squared plus 5x and we added 5 halves squared. And so now when we try to factor this again is x squared plus 5x plus 25 fourths. Factoring this is a little tricky, but I think you're going to find the pattern soon, which is x plus 5 halves times x plus 5 halves, which is x plus 5 halves squared. You'll notice as you do more and more of these that this number is always half of your b value. So geometrically here, we just shaved off half of our known part, flipped it, and then added in another piece which turned out to be half of that known part squared to complete the square. And likewise, algebraically, we took our b value, we cut it in half, and we squared it and added it to the equation to complete the square. Now I said make sure we keep the equation balanced. I didn't do that, so let me do that here. So here I had area, and since I added 5 halves squared to both sides, I need to add it, or I added to one side, I need to add it to both sides. And so that carries down, and I have a plus 25 fourths here, but I want to get a alone. So the area is actually x plus 5 halves squared minus 25 fourths. And you'll notice that that's now in vertex form, and there's lots of good things we can do with that. We could maximize area, we could find the biggest area, we could find the points where we'll have no area, which will just tell you the constraints of how big x or how big or small x can be. Lots of cool stuff.